in the last lecture, we basically discuss about the combustion, which is very important, because for any propulsive device the energy conversion will be taking place in the combustor itself. That is why I call it is the heart of any engine. That means, combustor is the heart of any engine, and we need to understand the processes involved in combustion, which is quite complex in nature, as I had depicted through a pictures by saying that it involves several other disciplines as well. So, what we will do? We will also now look at thermodynamics of combustion, which you might have learned, but for the sake of what you call repetition or completeness sake, and also to help you to recapitulate what you have already learned, and we will now indulge in it. If you look at like combustion always involve chemical reactions. Chemical reaction, what we will be considering basically a methane. That means, 1 mole of methane is reacting with the 1 mole of oxidizer, right, and it is going to what, like it is going to the water and carbon dioxide and certain amount of heat being released, right. That is the amount of heat which is being released. Now, question arises, is this reaction really balanced? Number 1, and why we need to look at really whether it is balanced or not, and what is the meaning of a reaction being balanced, right. Is this, if we just look at this reaction, what I have written down here, is it balanced? What is the meaning of balance? Balance means, if I look at in the left hand side, that is methane reacting with oxygen, right. Okay. I need to look at whether the elements, for example, in methane the elements will be, one is carbon, other is hydrogen, right. Whether it is same as that of whatever is there in the right hand side, that either in the carbon dioxide or in the water. That is the meaning of balance. In this case, it is very clearly being, you can see that it is not balanced, right. And if you want to balance, what you will have to do? You will have to basically take elements and balance it, right. And the balance equation would be 1 mole of methane is reacting with 2 moles of oxidizer going to the 2 moles of water and 1 moles of carbon dioxide, of course, certain amount of heat being released, right. This kind of equation you might have been taught from your high school. One question I would like to ask, whether this reaction really take place in nature or not. Can anybody tell me whether it is similarly it is occurring or not? It cannot be really occurred in nature. We will see little later on when we are talking about chemical kinetics, right. So, what is the meaning of this reaction? What we are saying, this reaction is balanced, that is 1 mole of methane is reacting 2 moles of oxidizer and going to the product as 2 moles of water and 1 moles of carbon dioxide. That means, what you are saying? You are saying that in the left hand side there are 3 moles of are there, and the right hand side this is 3 moles. Can I call it as a balance? That means, in other words, if the number of moles of the participating species is same as that of the right hand side, can I call it as a balance? Yes or no? But in this case it is looks to be like that, which is right. Actually, if you look at, we will be looking at whether the moles is balanced, number of moles in the left hand side of the various participating species, and the product number of moles, or we will have to look at mass. So, let us consider that what happens to the mass. Mass, if you look at, the 16 grams of methane is reacting with 64 grams of oxygen. It is going to the product 36 grams of water and 44 grams of carbon dioxide. What it indicates in the left hand side, it is how many grams? It is something 80 grams on the left hand side. If you look at this is something 80 grams and this side is also 80 grams, right. That means, what is indicates? It indicates that mass is conserved, right. That means, the mass, no mass is created or destroyed in a chemical reaction, only the change in their forms take place, right. In other words, mass is conserved, right. Is it really true? Because it says, I mean, we have done that. That means, it definitely it will be true, but is it not that contradicting the your what Einstein told, energy can be converted into the mass and mass can be converted into energy, but here there is a amount of heat, energy is there. So, naturally this is violating, am I right? That means, this is not right, or the what Einstein had told is not right. Can anybody tell me how come it is not satisfying the concept or the given by the Nobel laureate Einstein? What might be the reason?
Mass change is very negligible, sir.
Yes, that means, in this case the mass change will be negligibly small, right, such that you cannot really measure, right. And if you want to look at that, some example is given in my thermodynamics book, you can look at it, right. Because the amount of heat release is very, very small to have any tangible change in the mass, right. So, therefore, both are valid, and generally we use air as an oxidizer most of the combustions. Of course, in recent times there are some combustions people are talking about to avoid NOx and other things, that oxygen combustion kind of thing. But however, we will be using mostly the air as an oxidizer. So, if you look at this reaction can be written as the 1 mole of methane is reacting with the 2 moles of air, and keep in mind that we are considering only the air, means nitrogen and oxygen, others are negligible, and it is going to the carbon dioxide, 1 mole of carbon dioxide and 2 moles of the water, and large amount of 7.52 moles of nitrogen, right. So, what I would like to suggest that although we have seen in these equations and also in this equation that number of moles in the left hand side of the participating species is equal to the number of moles of the product in case of methane, but it need not to be true for other hydrocarbon, it is just a coincidence, right. That means, if a equation is balanced, need not to be that one can assume that the number of moles in the left hand side is same as the number of moles in the product, right, that you should keep in mind. So, now question arises, what is stoichiometric? Because we have talked about balance equation, right. That means, it will be related to the balance equation. What is the meaning of that? That meaning is that the ratio of the oxidizer to fuel, which is sufficient to burn certain amount of fuel leading to the complete formation of products of combustion. That means, if I am taking like 1 mole of the methane, it is reacting with the 2 moles of oxidizer, right. That means, it will be going to the product, that is what carbon dioxide and water, right. For example, if I take a CXHY, if you look at this is the generic name, generic formula for a hydrocarbon. That means, if I take x is equal to 1 and y will be what 4, then it becomes CH4, If I take x is equal to 2 and H is 6, that will be ethane, right. Methane, like x is 3 and H is 8, that become propane. So, if I react, I mean if I take a mole of generic hydrocarbons and reacting with A moles of air, right, and it is going to the x moles of carbon dioxide and y by 2 moles of water and 3.76 A into A, of course, nitrogen, right. This is generic I have written. That means, if you look at the fuel oxidizer ratio, which will give the product, like that means complete conversion of fuel into their respective product, like in case of hydrocarbon, all the carbon in the fuel will be converted into carbon dioxide, and all the water will be, all the hydrogen will be converted into water, right. Of course, oxygen will be there. Then we call it as a complete combustion product. There might be cases where the product will be containing excess oxygen. It might be containing certain amount of carbon monoxide, right. Can we call it as a complete reaction is complete? Certainly no, right. So, that means, what is the ratio of oxidizer to fuel, or in other words fuel to oxidizer, which is sufficient to burn a 1 kg of fuel, leading to the formation of the complete products of combustion? We call it as a stoichiometric. So, in this valence equation, where A is equal to x plus y by 4, right. Of course, if I take a methane, what will happen to the A? If I take x as 1 and y is basically 4, that becomes A becomes for methane this 4, A will be what you call 1 plus what you call 4 by 4 is equal to 2. We have seen in the last slide that A turns out to be 2 for methane. So, air by fuel stoichiometric, what we call mass of oxidizer divided by mass of fuel, and with happens to be 4.76 A molecular weight of air. This is molecular weight, right, MW of air, and similarly MW fuel is the molecular weight of fuel. And for methane air mixture, the A by fuel stoichiometric happens to be 17.11, whereas for others hydrocarbons it will be around 15. Do not think that it will be exactly 15, in some cases it will be 14.9, or in some cases it may be 15.2, right. Most of the hydrocarbons will be around 15 except methane. Therefore, this number is a ballpark number what we keep in mind, but exceptional case is methane, right. Now, when you talk about this air fuel ratio, it is basically non-dimensional number, right. Kg of fuel by kg of oxidizer, if it is fuel to air. If it is other way around, this will be kg of oxidizer divided by kg of fuel, right, if it is air fuel ratio. Now, but sometimes we need to know how far this air fuel ratio from the stoichiometric. In real situation, you need not to really operate at stoichiometric, rather we always try to operate at the lean condition, so that enough oxygen will be there, so that complete combustion can take place. Ideally, at stoichiometric all the fuel will be converted into their respective product, but in real situation it will not occur, right. And sometimes we need to also go for a less amount of air or the oxidizer as compared to the stoichiometric requirement, right. Particularly when we will be trying to get some pyrolysis products, right, or a gasify. For example, I want to gasify a fuel, solid fuel or some liquid fuel, naturally I will have to use less amount of oxidizer. You know, like we do that, like we will be starving. Starving in the means, suppose somebody asks me a question, I do not give the answer, I will just give the hint, so that he will think and get the answer, so that he will develop his mind instead of just remembering, listening to my answer and remembering. That is the way we should teach, not that give the answer, right. So, similarly, if I want to convert certain fuel, liquid fuel into a certain gaseous fuel or a product, better one, I need to be throttling, choking, but in a controlled manner, right, is very important. Like generally people always happy whoever will give answer, but I say that those teachers who give answer to the student directly, they spoil the students. So, similarly in this way, like you need to have a lower air fuel ratio, or depending on situations, you know, to have a conversion product. So, now we need to define how far this air fuel ratio is differing from the stoichiometric, right, because stoichiometric is the ideal or the theoretical air fuel ratio which is required for complete combustion. So, therefore, I need to define an equivalence ratio, that is basically a ratio of air by fuel stoichiometric divided by air by fuel. In other words, fuel by air divided by fuel by air stoichiometric. It can be lean mixtures, it can be rich mixtures. If I say phi is less than 1, I call it as a lean mixture. What kind of lean it is? It will be fuel lean. If phi is equal to 1, that is stoichiometric, right. Phi is equal to 1, stoichiometric mixture. If phi is greater than 1, that is what you call fuel rich mixture, which we will be using it. So, you should keep in mind, if phi is greater than 1, what is the meaning, and phi is equal to 1 is basically stoichiometric. And beside this, sometimes we will be using that what is the percentage of stoichiometric air, that is 100% divided by phi will give me whether it is higher amount of oxidizer or higher amount or less amount of oxidizer as compared to stoichiometric, right. Is this clear what I am talking about, right? Fuel lean, fuel rich and stoichiometric, like depending upon whether phi is less than 1 or phi is greater than 1. So, now we will take an example, right, that is the gasoline, what is being modeled as a octane C8H18 is burned with dry air. Keep in mind that gasoline is what we use as a petrol, right, in our petrol engines. And the volumetric analysis of the product on dry basis, right, one can obtain CO2 10.02%, oxygen is 5.6% and carbon dioxide is 0.88%, nitrogen is 83.48%. But how we will get this thing, right? You need to measure these values by using gas analyzers. Earlier days Orsat apparatus being used, right, you might be aware. Orsat apparatus by chemical means wet chemicals, right, means, and nowadays of course very good sensors are available, you can measure it. And suppose these are given, now we need to determine from this product what is this air fuel ratio and equivalence ratio and percentage of stoichiometric air being used, right. Let us look at how we will go about it. What we will do, we will have to basically look at a what you call equation what we started with, that is x moles of the octane is reacting A moles of air, and these are the product like carbon dioxide which is given, CO and oxygen is given and nitrogen is given, but water is not given, or water will definitely come, am I right, because it is a hydrocarbon, hydrogen is there. So, product must be having hydrogen. So, that is amount is not given, we will say let it be B, right. Then what I will do, I will have to basically balance. Can I just look at do it? Of course, some of you can do it if you are having good concentration and mind power, you can do that, but you may sometimes make some mistake. So, therefore, we need to do in a very systematic manner. The one which I am going to illustrate is basically we will be doing a mass balance, right. That means, what I will do? I will look at each element. For example, nitrogen is here, right. I will look at nitrogen 3.76 into 2, because N2, and A is the coefficient, right. I can say on the left hand side, right hand side will be what? Right hand will be 83.48 into 2. So, if I just take this balance, A happens to be A is equal to 22.2. And similarly, for carbon, if you look at, we are having 8 8x in the left hand side is equal to 10.02 plus, because CO2, and for carbon monoxide it is 0.88, I can get x is equal to 1.36. And similarly, for hydrogen in the left hand side is 18x, of course, in this place is not there, and water will be there, that is 2H, 2B, right. This will be 2B from the water. So, B will be 12.24 if you get that. And oxygen you can look at, because oxygen is there 2A, and then in this case from the carbon dioxide it will be 10.02 into 2 plus 0.88 from the carbon monoxide, and of course, from extra oxygen is there here. Here it is not a stoichiometric mixture, right, because carbon monoxide is there and also the extra oxygen is there. So, that will be 2 into 5.6 plus B, of course, in water there is a B moles will be there, right. So, then after that you will of course, get some values, that is B 12.24, and then you have already know these things, and you can cross check like whether the left hand side is same as that of the right hand side for the O. If it is, then you can say it is basically it is just to cross check. You may avoid it sometimes, but how will cross check it, that is given here. So, if you cross check that, and then sure that it is well balanced, the above balance equation will be like this, that is 1.36, we have already seen x, and of course, 22.2, that is our A, and then B is 22.24. That means, I can rewrite this equation in terms of 1 mole. What I have done, I have just divided by 1.36, and all those things I have divided by 1.36, right, and then I have written down like this. So, then air fuel ratio by mass becomes what from the actual, because this is actual, this is not stoichiometric. So, that will be mass of air divided mass of fuel, you will find that it is something 20.19, because all those things we are doing, right. Okay, all values we know, we can just put it, because this is the air, right. If you look at this is air, and this is nothing but fuel. So, I will get 20.19. Now, I need to, because air fuel ratio A we have found out, right. We need to find out equivalence ratio. For that, what we will have to do? We need to know what is the stoichiometric air by fuel. Like stoichiometric air fuel can be found out considering a balance equation, that is C8H8 12.5 O2 plus 3.72. It is going to product carbon dioxide, water, and of course, 47 nitrogen, right. You keep in mind that there is no carbon dioxide in the product, there is no extra oxygen in the product. That means, all is converted into carbon dioxide, all the fuel is converted into carbon dioxide, and of course, the water. So, this is our stoichiometric reaction. So, the stoichiometric fuel air ratio, if you look at MF by MA, and this is nothing but your fuel, and this is your air, and you will get 0.06643. Keep in mind that do not remove the decimal point, because it will incur some error, right. So, and if you look at what is this air fuel by stoichiometric, just to have a feel, it happens to be 15.05. As I told you, it will be around 15, right. Sometimes in the exam or somewhere you have land in some other number, please check whether it is around 15 or not, right. That is the except methane air or methane oxide. So, the equivalence ratio becomes what is that A by fuel stoichiometry divided by A by fuel, and you will find that it amounts to be 0.745. What is this? Whether it is a fuel lean or fuel rich. Here phi is less than 1. So, therefore, it is fuel lean mixture, right. If it is phi is greater than 1, then it is fuel rich mixture. It is because less amount of what you call fuel as compared to the stoichiometric oxidizer requirement, right. So, therefore, it is a fuel lean mixtures, and hence, so let us calculate the percentage of stoichiometric, that is 100 divided by phi, that happens to be 134.2 percentage. So, now if you look at like in the combustion, we have seen that we will be dealing with various mixtures of gases, right. That means, we have seen that carbon dioxide, water, what you call fuel hydrocarbons, oxygen, carbon monoxide, lot of gases will be there, right, both on the reactant and the product, sometimes the mixtures. Now, how we will deal with whether we can consider this to be ideal gas or not, and if we will consider it as an ideal gas, how to handle, if it is real, how we will handle the mixture of gases, right. That is a very important concept, which you must be knowing all those things what I am going to talk about it, right, because we need to handle this mixture of gases. So, question arises, what are the methods to be used to specify composition of a mixture, right. What are the ways? There are two ways of specifying a mixture composition, right. One is based on mass, that is mass analysis, other is molar analysis or number of moles, right. So, mass analysis of a mixture of gases, one can think of as let us consider a container which contains certain amount of gases, for example, carbon dioxide, methane, oxygen and other things, right. Or let us consider a container which will be containing a what to call certain kg of a gas A, and then maybe another gas B and C like that, right. So, I can find out the total mass of the mixture is equal to sum of the masses of the constituent gases, which can be expressed as that m is equal to m A plus m B plus m C, and there are n number of gases. So, I can write down m n, and I can write this in a compact form, that is summation of m I, where I is equal to 1 to n. It can be anything. For example, if it contains carbon dioxide, water and carbon monoxide and nitrogen, 4 gases, here it will be I is equal to 1 to 4, right. And if I divide this equation by mass of mixture, similarly here, right, mass of mixture, what will happen? This will equal to 1, and m A by m mixture, right, we can write down as m 1 is equal to m A by m m plus m B by m m plus m C by m m up to the m n by m I, and I can write down that is in a compact form m I divided by m m. And what is this term? This is nothing but your mass fraction, right. So, I can write down mass fraction of ith species, right, is equal to, we can use a symbol x I is equal to m I divided by m m. Now, if I use this symbol and write down in this expression, what I will get is 1 is equal to x A plus x B plus x C up to the x n summation of x I. What it is saying? That mass fraction of all the participating species or all the species in a mixture is equal to 1. This is a very important concept which you will be using several times, and this you should keep in mind. So, similarly, we will be looking at mole also, like let us consider a container which contains certain amount of mixtures gases, and let us say Na moles, Nb moles and Nc moles, like that. Then we can look at that total number of moles in the mixture, that is Nm, is equal to sum of number of moles of each constituent of the mixture, that can be expressed mathematically as Nm is equal to Na plus Nb plus Nc summation up to the Nn, and I can write down summation of Ni, right, where I is equal to 1 to n. If I divide this by Nm by Nm here, and similar way I can write down this expression as 1 N A divided by N m, N b by N m up to the N n by N m, and keep in mind that this can be written that summation of N I by N m, and if I can define this as a mole fraction of ith mixture is equal to Y I, is nothing but N I by N m. So, we can write down that in a similar expression, that is Y a plus Y b plus Y c I mean like till Y n and summation of Y. What is indicate that mole fraction of a mixture, sum of mole fraction of all the constituents in a mixture is equal to 1. But the mass M I can be related to mole, right, of course, with the help of molecular weight M W I, and because we know that M I is equal to N I M W I is the ith species, right. It can be carbon monoxide, it can be oxygen, it can be any other species, I means any species. Okay. So, then I can write down M m is summation of M I and is equal to, because I will just use in this expression N A M W A plus N B M W B and till nth and M W M. In a compact form I can write N I M W I. If you look at I is equal to 1 to n, right. And if I divide this by the N m, like this expression N m, similarly all this expression by N m, if you look at, I can write down in this way, that is summation of N I M W I N m. And what is this term? This term by definition it is Y I. So, I can write down, and what is this term? This term is basically the M W M, that is molecular weight of the mixture is basically sum of the product of mole fraction of gases like A into molecular weight of gas A, that means respective molecular weight, and sum over that will give me the molecular weight of the mixture. This is very important statements which you should keep in mind. Suppose there are several gases, individual molecular weight I know, then I need to use this mole fraction to find out what will be the total molecular weight of the mixture or the right. So, but X I we know by definition M I by M m, and we know that M I is nothing but your N I and M W I can write down, and this is nothing but your Y I. So, I can write down that X I is equal to Y I M W I divided by M W M. That means, if I know the mole fraction, I can find out mass fraction, provided I know the molecular weight of particular species and also the molecular weight of the mixture. That means, this can be related to one another following expression. This is a very important expression you should keep in mind, right. So, now we need to look at behavior of ideal gas, whether we can consider ideal gas or we need to consider this combustion products and then mixtures kind of things as a real gas. Is it possible we can assume to be ideal gas? Most of the times we use ideal gas. Why? Because the temperature will be very high. Of course, the pressure also in case of rocket engine particularly will be high. So, as the temperature is quite high and pressure also is equally high, we can consider not really incurring too much of an error, particularly in rocket engines for the simplicity, but other cases you can happily use ideal gas mixtures, right. Now, question arises, if I take this air, right, and what will be the pressure and at which we can consider the gas as an ideal. If I take a pressure air simply, let us take air, what will be the pressure at which we can consider to be gas as a non ideal, right, or I cannot apply. Do you know this thing? For that you need to recall or the relearn about the compressibility chart, right. I will just give you the hints that around 100 atmospheric pressure at ambient temperature, I can happily consider it to be ideal gas without really incurring too much of error, right. So, 100 atmospheric pressure is a quite a bit, right. Most of the your gas turbine engines, we do not go to that high pressure, right, and temperature is high. Therefore, we can happily use for combustion processes ideal gas and use it. So, therefore, we need to know that, and for ideal gas we know P v is equal to N RUT, RU is the universal gas constant, and can you use ideal gas law when two or more ideal gas are mixed? This is a very important question, because if in the mixture carbon monoxide is there and nitrogen is there, right, or carbon dioxide is there as well. So, whether each individual can be considered an ideal gas, but can I consider, right, as an ideal gas, right, total mixture, that is important. So, it can be done only when that each individual composition behave as an ideal gas. For example, like air, which consists of several ideal gases like oxygen, nitrogen, argon, carbon dioxide, right, and extra, can be treated as an ideal gas, provided the composition behaves individually as an ideal gas. That is very important, right. So, then under this condition we can use the mixture to be an ideal gas, and then the mixture can be conveniently analyzed mainly by two models, namely one is Dalton model and other is Amagat model. So, the pressure of an ideal gas mixture is equal to sum of the pressure its individual components would exert if each existed alone at the same volume and temperature of the mixture. This is nothing but your Dalton's law of additive pressure, which you have learnt from the school days as well. Let us look at pictorial. I have shown here what is saying the air contains nitrogen, oxygen and argon. It is having the same volume and same temperature T A, right, but whereas the pressure will be different, and these pressures of individual gases exerted if each alone at the same volume and the same temperature of the mixture, then we call it as a partial pressure, right. So, if you look at, if I take this pressure mixture by using ideal gas law, Nm Ru T m divided by V m, all these symbol. V is the volume, T is the temperature, N is the number of moles of the mixture. Then I can write down, we know that Nm is equal to Na plus Nb plus up to the Nn. then I can regroup this and write down Na RUTM divided by Vm, and this is, and similarly Nb RUTM by Vm, and all those things. If you look at, this is nothing but what? That is P A. Similarly, this will be P B, right. That is the partial pressure of that. I can write out P A total pressure experienced by the mixture will be sum of the partial pressure, right. And for this example, what I have taken air, it will be P A, the partial pressure of nitrogen plus partial pressure of oxygen and argon, right. That is basically Dalton's law of additive pressure, what we will be considering. And now, let us move at what is the limitation of this Dalton law of partial pressure, So, if you look at Dalton law, assume that molecules of individual component are not influenced by the pressure of other components of the mixture, right. This is an assumption. So, therefore, in a real situation this assumption may not be true, because right, and other one is that Dalton's law is valid only for an ideal gas mixture. Of course, you can apply this for a real gas with a moderate errors within certain pressure and temperatures, right, range, because if it is a very high pressure and low temperature, then actually this will not be valid, and we will not be getting into that regime. And this is due to the fact that there will be significant intermolecular forces in the real gases at high pressure and low temperature, which are being neglected, in case of an ideal gas, hypothesis. So, and we need to look at this Amagat's law of additive volumes, which state that volume of an ideal gas mixture is equal to the sum of volume of each individual component gas that would occupy if each gas existed alone at the mixture temperature and pressure. In case of your Dalton's law of partial pressure, what we are considering? We are considering the temperature and volume to be same for the both mixture and each component. In this case, the temperature and pressure to be same, that means volume will be changing. For example, if I consider the air, total volume of the air which will be remaining same at the mixture temperature and same as the pressure will be equal to the volume of the nitrogen gas and oxygen gas and argon gas at the same temperature, mixture temperature and pressure. Keep in mind, that is very important one. So, if you look at mathematically, what is that? V m is equal to, again using ideal gas law, that is N m R U T m by P m, and N m in place of that I can write down N a plus N b plus up to the N n, right. And if I take separate out, if you look at, this is nothing but your V what you call A, right. Similarly, this will be V b, like that it goes on, right, V n. So, we can write down that V m's of the mixture will be summation of individual mixture of the gases, like or volume occupied by each gases in the mixture. So, if you look at V a is basically summation of the what you call V I, where 3 gases are there, nitrogen, oxygen and argons of the volume. These things we will be using basically to look at various other properties like enthalpy, entropy and other internal energy kind of things. So, let us look at relate these things, and if you look at the volume V a by V m, if I look at in place of V a using ideal gas law, I can write down N a R U T m divided by P m, and V m I can write down like that. If this will be cancelling out, if you look at this will cancel in, what is that? N a by N m is nothing but your mole fraction of the species A, right. And similarly, we can look at partial pressure P a by P m, and if I look at that, we can write down P a as N a R U T m divided by V m into V m divided by N m R U T m. So, this will cancel it out. What is that? This will cancel it out here. similarly it will cancel it, you will get Na by Nm, which is nothing but your mole fraction of A, and which is equal to V A by V m, right. What it indicates? It indicates that the pressure ratio, right, or pressure fraction is equal to the mole fraction is equal to the volume fraction, of course, only for an ideal gas. This is a very important concept which you must keep in mind. Now, for mixture of 3 ideal gases, namely A, B, C, we can write down M m is equal to M b plus M A plus M b plus M c. Similarly, N m in terms of number of moles, N m is equal to N A plus N b plus N c, and I can write down basically P m is equal to P A plus P b plus P c. This is from the Dalton's law of partial pressure. So, from the Amagat's law, I can write down V m is equal to V A plus V b plus V c, right. I can use that, and we can write down this internal energy U m is basically U A plus U b plus U c, and summation of that in the 3 spaces. And if I look at the specific internal energy, it can be either for the like U m is summation of y I E y, n I of course, the function of this, right. And similarly, I can write down for enthalpy, which is summation of mole fraction and H I, right. That means, using this concept, I can estimate what will be the entropy of the mixtures and also the specific entropy in terms of mole fraction of the ith species, or it can be summation over 1 to n. For 3 species, you can write down A, B, C like that. And now, let us look at about enthalpy, because we will be dealing with enthalpy, right. Let us look at enthalpies kind of thing. So, specific enthalpy of the mixture is given a mixture. I am just writing to specify X I H I cap. Keep in mind that this is enthalpy per kg of fuel. That means, enthalpy is a kilojoule per kg. This unit will be kilojoule per kg with a cap, and without cap, that is kilojoule per kilomole kind of thing. Similarly, and for this case, you will have to use the mass fraction, and H mixture you will use the mole fraction and H I, where this enthalpy of a species can be expressed as H I T is equal to H F with respect to the standard, that is 298.15, and the atmospheric pressure, that is 0, plus Cp I dt. What do you call this term? This term is nothing but your heat of formation, right. HFI, this is nothing heat of formation, and Cp I dt, which will be integrated 298.15 to the particular temperature, will be basically sensible enthalpy, right. So, this heat of formation you can get from a tables. Of course, it has been made from using the concept of reactions. So, which I will not be getting into, but we can look at like how to calculate this heat of reaction and formations, right. And we let us consider that 1 mole of methane is reacting with 2 moles of oxygen going to the product CO2 and water at 25 degrees Celsius and 0.1 megapascal. Keep in mind that this is also there. That means, both the reactant and product are at the same temperature, although the some heat being will be released in that. That is the assumptions. So, if I use this and also make some assumption that steady flow process, keep in mind this is the process and this is your CV, and steady flow process, no shaft work, like change in kinetic energy is 0, change in potential energy is 0, and there is no shaft work, and you will find that Q is nothing but your H p minus H r, and where H p is summation of N I p H I p, P is the basically product, and I will be any number of species, and similarly minus N I r H I r, R is the reactant. And keep in mind that this portion is known as the heat of reaction at standard state. What is the standard state? That is 298.15. This we call is heat of reaction, right. And this heat of formation, like per unit mole of either the reactant or for any species, you can use for the table. I will just show you that various tables will be available. You can see that oxygen heat of formation is 0, hydrogen will be oxygen will be 0 and nitrogen will be 0, and water, if you look at gas, it is minus 242 kilojoule per mole, whereas for the liquid it is 286 kilojoule per mole. What I was talking about low heating value and high heating value in the last lecture. Similarly, kerosene it can be 51.6 and which is in liquid state, right. So, you can use this table to estimate the, and what is the meaning of this heat of reaction. Basically, if you look at the reactant will be at here in this zone. This is, keep in mind that enthalpy versus temperature is being plotted, like at various temperature it is changing, which indicates that the heat of formation will be changing with the temperature as well. Similarly, the product and this difference is nothing but your heat of reaction, because you are considering at this point of the standard temperatures, and the variation of heat of reaction and product with temperature which I have already told. And although it is being drawn parallel, but in real situation it will not be parallel, keep in mind, right. It will be different, because the Cp is a function of temperature, right, that you should keep in mind. So, let us take an example, like 1 mole of methane is reacted to oxygen is stoichiometric ratio, consider the heat of reactants at temperature of 298 Kelvin, and pressure, of course, this is standard pressure, determine the heat of combustion, right. How will determine the heat of combustion? We will have to basically look at heat of the reactions, and then heat of reaction will be negative, because it is the exothermic reaction. So, then we will divide the mass of the fuel kind of thing, we will get the heat of reaction. So, stoichiometric reaction is given below, that is methane reacting with 2 oxygen, going to the carbon dioxide and water. So, from this heat of reaction I can get, I can write down here, this I can get from the table, right, heat of formation, and similarly oxygen, of course, this will be 0, right, this will be 0 heat of formation of oxygen. And if I will substitute these values from the table, like for heat of formation for carbon dioxide, for water, and then you need to use this heat of formation problem, whether it is a gas or a liquid, that is very important. And similarly, for the methane, you will have put substitute these values. When you put this thing, you will get minus 803.5 kilojoule, keep in mind that. And heat of combustion will be heat of reaction, of course, the minus sign of that became positive, divide by mass of fuel. In this case 1 mole you can put into molecular weight, and you will get 50.2 megajoule of heat being generated when you burn 1 kg of fuel. With this I will stop over. Okay. Do you have any question to be asked, any doubt?